coupling is given. Collector of that transistor which is off is connected to the base of the other transistor which is on in monostable case, and output is taken at the collector of the. Just revised it for your sake of continuity. As far as the emitter coupled is concerned, that I have done for bistable multivibrator, which I named as Schmidt trigger circuit. So bistable operation I have shown in your class, that is your again two transistors, but one of the base is open. There no feedback is given. And that is the advantage this Schmidt trigger has got. So it is not controlled by any of the signals available in the multivibrator. It is controlled by the trigger directly. And that's why that is the advantage, that it will not allow this transistor which is off to go into saturation. It will switch from off state to active state. And at the same time, the transistor which is on, that is switched between on state to active state. That is the advantage. None of them is going to the saturation stage in your Schmidt trigger circuit. So today I will talk of emitter coupled multi, and I'll try to complete that in 25 minutes or so. Professor Sen Gupta is there, I think. Is he there? Professor Sen Gupta, are you there? It's not seen. Okay, he was there, he scheduled the class. Anyway, if he comes, we may discuss something on the operational amplifier based designs that we have done in the case of your 555 timer, IC 555 timer that you have seen. So that can also be used as astable multivibrator, monostable multivibrator, also as bistable multivibrator. So that is Schmidt trigger, emitter coupled monostable, emitter coupled astable. All three are possible with your IC 555 also. So this is the one I want to talk today, and that will be the completion of the module number 3. So I'll take some examples also in due course of time for your sake of convenience. Okay, so I take the presentation in my hand and let me complete this trigger part. I will start with the introduction of your Schmidt trigger, that is bistable, emitter coupled bistable multivibrator, that I have already done. And I'll say what way it is becoming astable and monostable in due course of time. Okay? Anybody, any query from the collector coupled ones or Schmidt trigger? Please raise. Okay, fine. I'm going for the presentation now. Yeah, I am presenting the multivibrator, two NOT gates connected. Here also NOT gates are connected. I'll consider transistor because you have got a lot of discussion on transistor, dependent multis, etc. This is my collector, this is my emitter, and emitter is not grounded, it is coming here. Okay. Similarly, this transistor is also there. This is the base. This is the thing. And this emitter is also not grounded, it is coming here. Okay. Then our supply is same thing as your VCC. This is my VCC because it's NPN transistor. So it is your V plus VCC. Now, as usual, this base of this is my Q2, for example. I'm talking of bistable. This is my Q2. This is my transistor Q1. Okay, so this base is not kept open because this is considered to be on. The way we proceed the design, that I switch it for infinite time, this will become on. So that means here I am considering VC2 on. That means at infinity. Infinity means this is your on, okay? And this is connected by a resistance to this base. And here, as I said, we are requiring one negative supply. So that negative supply will not be needed because this base is open and trigger is applied here. This we are making it very close to saturation, not deep inside the saturation. So this negative supply is not needed here. Earlier case, we are needing this to bring this Q2 into deep into saturation, and then we are operating that. That was the one which was avoided by making a negative supply here. So this we are not putting. This I will just ground it here. Okay, so I'm putting this one as my R1. This one I'm putting my R2. Same thing as your collector coupled case. This is my RC symmetric. It is symmetric. You can make it asymmetric also, but that is no use for the bistable case. So it is your RC and RC, both the cases coming like that. This emitter, both of them I ground through a resistance here. Grounded through a resistance, I call this as my RE. Okay, this RE voltage will be rising and decreasing according to the current flowing through it. Okay, this is open. I call it the place where this trigger, positive trigger is applied. Positive trigger is applied. Positive. When the positive trigger is applied, this becomes active region. Earlier it was off. So from off it will come to active region now. It will not go to saturation. And that voltage coming here will be transferred to this base as a Thevenin's equivalent of this one. And this base, when this has gone in active region, this potential decreases. That decrease in potential comes here. So this decreases such that it becomes, it was on now, it comes to your active region, not to the cutoff. It will come to the active region. It can go to cutoff also, doesn't matter. So you can say it becomes on and off both. Or even if it is active region, analysis will not change. I want voltage to rise here. Okay, so it comes to active region. This voltage is small. Now active region current flowing will be less than the saturation current. So this voltage will be higher because drop it across RC will be less. Okay, so this voltage will be higher. So that way it will change the state. So R1 and R2 are biased such that it is biased very close to the V gamma. Okay, so V gamma in active, when the pulse is applied, at that time it will come, it will fall, it will come to the something close to your V gamma that will make it off or it will make it active region according to that we are choosing over here. Okay, so this is the way it is working. Now this has come, this has become now active or off, whatever you say, this voltage has risen. Okay, so VC2, now I am finding VC2 0 plus. So this one will be how much now? This will be VE plus VE means VRE. Okay, across RE, that is my VE. So it will be a VE plus VCE. If it is off state, it will become your open circuit. That way I can say VE plus VCE. Okay, whole thing subtracted from VCC. No, sorry, no subtraction required. VE plus VCE becomes your VC2 0 plus. Okay, how much is your VCE? Okay, that is depending on the biasing of this thing. So anyway, this voltage has gone up, VE plus VCE. VE has increased, means what? VE is nothing but IC2 plus IC2 by HFE, IB2. When it has gone in active region, IC2 plus IC2 by HFE into RE. So this voltage has increased, RE has increased. Okay, and that way this output voltage increase. What happens here? This RE has increased, so this trigger is gone now. 0 plus it applied, now it is gone. So this voltage is now decreased between base to emitter. The voltage is decreased. As a result, this will start returning back to your cutoff state again from the active state. From the active state, it will start returning back to your cutoff state because it will be gradually rising. Okay, it will be rising now. When current has flown through this, it has risen now, and after that, it will come to your cutoff state, and this will come to your saturation state. Okay, so that is there. So when this is applied, first trigger is applied, T equal to 0 plus, my VC2 at 0 plus becomes high, and VC1 at 0 plus becomes low. Okay, this both of them can be defined according to their active regions also like that. Now what happens? It will remain as such until unless the second trigger is applied. Okay, until the second trigger comes, it remains in this state. VC2 remains high, VC0 plus remains your low. When the second trigger comes, second trigger has to apply. One sec. This has come, this has increased, this has gone to your off. Oh, this has gone to on, sorry, this voltage increase, so a VC1 is on. So this has become your on, this has become your off. When this has become your on, this current increases, this voltage decreases, that is fine. When the second trigger is applied, this has to be applied as a negative trigger in that case. This will become once again off. When this becomes your off, accordingly this will become your on. So positive and negative trigger has to come at this point. Or you can say trigger should go at this base and this base. That is not advisable. Trigger is coming here, and in this trigger, it is changing the state. So when the next trigger is coming, we'll try to bring that in the form of the negative trigger, and that will be changing the state of that one. So this trigger has changed the state. Yeah, I think second trigger also should change the state. Why it is happening like that? When the trigger comes, yeah, sorry, now we know. When the trigger comes, this voltage will now increase. Positive trigger, second trigger is also positive trigger. When the second trigger comes, between this and this, the voltage increases. When this voltage increases, this will be, earlier VE or RE was increasing. Yes. this voltage decrease. When this voltage decrease, this became your on state. Now when this is applied, emitter to base voltage has gone up now. When this has gone up, it becomes your more than, sorry, it's gone up. That means this difference is, it is NP and P and N. So N becomes more positive than this P. Okay. So it will become cut off now. It will make it cut off and switch will return to the once again similar state. So what is that? Second trigger should bring this one. What is that? When the second trigger coming here, this current increases, it decreases. One second. Trigger has come, this has changed the state. Now when the second trigger comes, it should change the state again. The second trigger has to be negative in that case. It becomes negative. This will become, trigger is positive. Positive trigger. Initially trigger appeared, T equal to 0 plus is coming like this is okay. And to remain in this state till the second trigger appears. When the second trigger appears, when second trigger appears, VC1 should become high. Second trigger should become off. It was active, high. Mistake. This becomes high. When this becomes high, emitter voltage should decrease in that case. Where is the mistake I have made? Mistakes here. Voltage. Second trigger, how does it control? First one has changed the state. It is changing a state from 0 to 1 and remains in 1 until unless it is controlled. Second trigger has to be, I think it has to be negative or it has to be given to this base. Otherwise it will not work as a binary. When the second trigger comes, it will change the state again and third trigger will apply here. I think that is the way it is going, but trigger, why trigger should be applied to this base? That is the question. So it's a negative trigger here itself. Positive and negative trigger should be given at this point itself. So it will be positive trigger and negative trigger given at this time itself. So second part must be inverted. Okay, anyway, I'll be back to it with some more information in other class. Coming to monostable. Monostable is having a capacitor, so that charging will be there. Monostable, same thing, same circuit is something like that. Here is your resistance. Here is your emitter. These emitters, both the emitters are grounded through this RE. And this base, as usual, in the collector coupled case, will be connected to a positive supply, not to a negative supply, not to the ground. As in collector coupled case I have made. So this becomes your R. Okay, this is your RE, RC, this is your RC. There is a capacitor here. And this capacitor is coupling to the base of it as it is. This base is kept open. This base is kept open, going like that. So base is not biased, this is your RE. That's it. So RC, R and RE. Only four resistances are coming like that. I'm taking output at this point. Here also, this is on, that is my Q2 is on in the stable state, and this is my off. This is my Q1. Now when a trigger is applied at the base, what happens? This becomes active region. This goes to active region. As a result, this voltage decreases. This voltage decreases and it is transferred to the base of Q2. The base of Q2 is decreasing because capacitor is not charged. So immediately it decreases. This goes into active region now. When the trigger is applied, this has gone to active region. This also comes to your active region. From on state, it comes to your active region. As a result, current through this RE will be increased. So it is here also you assume it is going from on and off, on to off. When the trigger is applied here, this voltage becomes your on. So drop across this one will be very high. This voltage will become your something VCE or so, and that drop VCC, when it is off, the voltage of VCC and the current is flowing, VCC minus IR, that is the drop. So IR drop comes here. So V sigma minus IR is the voltage here. According to that, this has become your off. So here voltage becomes your VCC. This was my VCC. And it will remain on till what time? Till this duration. What is this duration? This duration is charging of the capacitor through this R and RC. That means what? This is at T equal to 0 plus, this is my Thevenin's. VC1 Thevenin's equivalent, and here is my R. C1 Thevenin's equivalent. Here is the capacitor. Here is my R. Here is my VCC. So that is the way this capacitor will be charged. So what is the time constant? R plus RC1 at T equal to 0 plus Thevenin's equivalent C into this thing becomes my tau. So e to the power minus t by tau is coming, and as usual, you have seen that it will be your 0.69 R dash into C. I cannot say RC in the earlier case also the same thing, R plus RC Thevenin's. What is RC Thevenin's? When you are T equal to 0 plus, this has become active region. This has gone to active region. Trigger is applied here. So at that time, your Thevenin's equivalent here will be very small. Okay, because this is open circuit cut from here. Thevenin's equivalent here, I want to see if it is cut from here, how much is the voltage coming at this point, and that voltage will be how much? VCC coming through R, so that will be VCC. So VC1TH will be VCC, Thevenin's equivalent. I have cut from here, given a cut here, it will become your VCC. What is your resistance? Thevenin's resistance here. At this point, I have given a cut here. So VCC and R is coming at this point, and parallel to this is R1 parallel to R2. R1 plus R2. RC parallel to R1 plus R2 becomes my Thevenin's equivalent resistance here. Oh, sorry. My goodness. I'm going to saw diagram. Here. Sorry. I have given a open circuit here. So VCC through RC is coming at this point. That is my VCC. Because Thevenin's equivalent, I have to see the supply, how much is coming over there. So RC. How much is my Thevenin's equivalent resistance? I have given a cut here. Voltage source is grounded. So it becomes your RC. So your VC RCTH, that is nothing but this is your RC. So it will be your tau will be C into R plus RC. RC Thevenin's equivalent is just like your RC. RC is small, answer goes like that. So 0.69 RC dash is what? R plus RC. R plus RC is coming as a resistance. In series you see, so it is your charging. So that is your 0.69 R dash, that is your R plus RC into C. So that way this monostable is working in the emitter coupled case also. So same thing here also, the base of the first transistor is kept open, and this is helping us from getting a feedback from the output here that will, enhance your delay, and it will, what to say? It will be affecting the circuit's output values also according to that. So by putting here, this is not taking part in any feedback condition. Similarly, I'll come to A stable. Similar circuit. A stable case, collector coupled. So I can say emitter coupled, emitter coupled multi-vibrator. What is that? It is same thing here. This base will be kept open. This is my resistance, RC. Here is my emitter. Okay. Second is coming like this. This emitter will be biased RE going like that. Okay. Now this is coming directly connected here. This is your VCC. See, this resistance I will split into two parts. So I'll put this in this R. I call it RE1, or you can say RE directly. Here also I will be having, I can say RE dash. So this is split into two parts. You can make it RE and RE here, but this is not connected now. This is not connected. Instead of that, it is connected by a capacitor. So two emitters are coupled. These two are grounded like that. And as usual, this base will be given a positive supply. So this is your R. So this R, this is my RC. If you want half duty cycle, then RC1 equal to RC2. Else T1 and T2 will be different. For time period equal to T1 plus T2. I'm coming to that. Which will be controlling your T1, which one will be controlling your T2. So your capacitor is coupling the two emitters. This is not there. This is your RE dash. What is RE dash, by the way? This RE was parallel combination of these two. Same identical resistance. So that means it becomes RE becomes how much? Parallel combination means half of RE dash. Okay. So this becomes your, earlier this RE was equivalent to half of RE dash. So that means if I realize that way, it will be your twice RE coming here, twice RE coming here. Okay. Would it be all right? It will be your R1, R2 divided by R1 plus R2 in parallel combination. Both are equal, becomes your R square by 2R. That is your R by 2. So parallel combination of R becomes R by 2. Okay, so this RE which you're taking. So you consider this as RE, this as RE, and try to see the operation of your A-stable multivibrator. Okay, what is this? This base is open here. I cannot keep it open, so I apply a voltage here, positive voltage VBB. VBB will be less than VCC, of course. So apply a DC voltage VBB here, it becomes your multivibrator, it will start oscillating. Look, this part is not there. This is cut and this is cut from here. Nothing, only capacitor is there. A VB DC supply is given. This is your RC. You can make it RC1. I can put it here RC1. I can make it RC2. T1, T2 will be different. This R will be a single one. This R will be connected, will be charging this capacitor by this circuit. It will be charging this capacitor by this circuit as well. So depending on what is the situation of the voltage at the emitter, it will choose its path, and both ways it will be charging. So according to that, your T1 and T2 in the AS table will be computed. What will control the T1? Suppose I'm taking voltage here, RC2. I'm taking voltage here, the V0. So this V0 will be high when? Assume this was your low, at t equal to 0 minus this was low, at t equal to infinity it was low, and this was high. Okay, so when this was low, at that time high current was flowing through this RC, okay, and that current was flowing through this transistor also. So RC, so VCC minus this voltage V0 divided by RC by the current which are flowing through this. It was flowing through this RE. It was charging the capacitor through this going to the ground. So it was having two paths. One is going like this, one was coming like this. So when it was on, it was low, it was charging by this path. As a result, this emitter voltage was decreasing. When the current was high, capacitor is charging now. So this voltage, whatever was here, that came here, whatever voltage came here, that appeared here. Now capacitor is charging through this RC2 and this RE. It is charging like that with this voltage, this potential. So you can say my T1 will be controlled by RC2, sorry, it will be T2. It is a T0 minus talking. 0 minus is coming, so T equal to 0 plus T2 will become high. So it is your RC2 plus RE RE dash I'm putting here into C. This becomes your tau, okay, into approximately 0.69. 0.69 into RC tau. So this becomes your T2. And after that, this emitter voltage has now reduced because this charging of the capacitor is subtracting from here that voltage, it is reduced. So it is reduced. This voltage is now coming close to your cutoff. So this will go to your active region or go to your cutoff. Sorry, it was in a saturation there or the active region there earlier. This was voltage here on has come to active now. And after that, this capacitor will bring this one to off. So from active region, from on it has come to an active region, sorry. It was on earlier, now it has gone to active region. And this VBB applied here. This voltage it becomes your now V your closer to V gamma, that is connected to this. This V gamma comes to this point, so this becomes your on. When this becomes your on from active, it has become your on now. When this becomes your on, it will be charging through this resistance, this on state, this capacitance, and this RE2. It will be charging the capacitor according to that. So this is your giving you your T1. It will be remaining high till the period T1. Okay, and that is your RC1 plus RE dash into C into 0.69. So T1 will be controlled by RC1. So different T1 and different T2 if you want, you make like that. RC1, you choose some RC1 for the same C, RC2 for the same C, your duty cycle will be changing according to that. So that is your emitter coupled multi. So instead of having two capacitors, only one capacitor is used. Okay, for a stable case, resistances are also somewhat reduced because the two collector resistance and single resistance is there. Yeah, these emitter resistances are coming as a additional components. So you can see this is the A stable multi-fat emitter coupled A stable multi-vibrator, which is your A stable. What is that? A stable. Remember, in all the discussions, I have assumed that at t equal to 0 plus, the Q2 t equal to 0 plus is on, sorry, 0 minus. 0 minus Q2 at 0 minus is on and Q1 0 minus is off. It is on, this is off. 0 minus is also, you can say it is infinity. When I have switched on, I have not operated. So Q2 at infinity is same thing, on, and Q1 at infinity is considered as off. But when I start my observation, at that time t equal to 0 plus starts, and you have to see that way what is going to happen after t equal to 0 plus onwards. So after T1, it will return from high state to low state. It will remain in low state till the interval T1. After that, up to T2 interval, it will remain in the low state. Again, it will go to the high state like that. So when it is t equal to 0 plus only, I think, when t equal to 0 plus, we'll see like that, yeah. T equal to 0 minus it like that, t equal to 0 plus, it will be changing. So this is your Q2 becomes active. And Q1 also becomes your active. So one is decreasing, one is increasing, and that way it will be swinging like that. So this is about our thing. Is Professor Sen Gupta there? Sen Gupta? Is he there? Am I audible to all of you? Students?
Yes, sir.
My network is not off. Now I'm
Yes.
giving a pause here. Professor Sen Gupta is not there, it seems. Is he there or not there? Sen Gupta is not there. Anyway, so I have done that. If there is a question, I can take as an example and tell you what to do. So this is the one that I wanted to say. Now let me see. I mean, what has happened there in how to go to that presentation now? How to go back? Okay, I'm here. Like your A stable, what way the voltage is changing? So I'll be giving you something in A stable, what way the voltage is changing. So let us say at T equal to 0 minus. Okay, Q1 is on and Q2 is off. So V C2 with respect to my ground is your VCC. I'm talking of A stable. A stable, emitter coupled. Okay. Similarly, V uh, E1. Okay. Because emitter of 1 will be how much? VBB minus V sigma. Is it okay? Sorry, VB minus V gamma. VBB applied to the base of Q1 and it was in cutoff, so VBB minus V gamma, it becomes my emitter voltage VE1. So what is my VC1? It is your VB2. The second transistor, the base potential, and that will be your VBB minus V sigma. What does it mean? Both times are identical, so your VC is saturation is the same for both of them. So VBB minus V sigma plus VCES, it coming at the collector of this one. That was in saturation, so base potential was your V sigma. Okay, base potential was your V sigma, base to emitter voltage was V sigma. Okay, and VE1 was VBB, sorry, VCES at T equal to 0 minus this was saturation, V sigma was the voltage there. Will it be VBB coming or what? VB2 VBB plus this was on, so C minus V sigma. No, it's not VBB, it is something else. Okay, my V sigma. There it will be your VCES plus, let me put this way, it will be your VCES plus VE2. Okay, VCES was VE2, and what is my VE2? VE2 is your VE2 will be equal to VE1. Because capacitor is fully charged. You charge or what? T equal to 0 minus, it has fallen down to that. So it will become VBB minus V gamma, not sigma. It will become V gamma then, sorry. VBB minus V gamma it will be there. It will be V gamma. Okay, fine. At T equal to T1, what happens? t equal to 0. VBB minus V gamma, VCES minus V sigma. E2 was your VBB minus V sigma. I think I'll do it in the next class. Okay. I'm getting confused somewhere. 0 plus and 0 minus. In the next class, I'll take my example from this place. I'll do that. Okay. So let us close it here. I will take as example how to compute voltages at various points in the A-stable multivibrator. Emitter coupled, collector coupled, of course you already know, but we'll revise that also in the example. So what to do? Should we switch off here? Should we take leave?
Yes.
Okay, so good day. I'll see you tomorrow. In tomorrow class, I'll take example here and take some more examples and so on like that. Your questions will be from this portion only. Computation of various voltages, various currents and all that. What is the voltage swing at the output? So these are the things will be asked on that. Okay? So good day. I'll take leave now.